Okay, here's the modified turbine. It's got a little bit narrower wing, and it reaches a peak a little bit closer to the outer perimeter. I chose the shape to be a little bit more like the torque turbine here, which is doing nicely, but it uses the same math as this one. This one, it's just got a higher starting slope at this edge, and it's like 120 degrees, so it has this big scoop here. So this one's got narrower scoops, and the high point is a little bit closer to the outside edge. Our wind is really light right now. I wanted to briefly go over the math used to create the profile for the drag turbines, and this is the way I figured it. I'm using polar coordinates, so there's theta from the x-axis and radius out to a point. And what I wanted was something that when, if the wing kind of had a curve like this, I wanted something that had a steep slope when theta was close to 0, and I wanted something with a shallow slope when theta was close to a certain maximum. And so if I wanted to plot that slope, dr, the change in the radius with the rd theta, change in this direction, there's the slope. So if when and then theta is on the x-axis, so when theta is small, I want the slope to be large, and when theta is large, I want the slope to be small. And I always want the slope positive. I just wanted to make sure that it kept decreasing. So one curve that accomplishes that is the rectangular hyperbola, where the slope is just some constant value a, it's arbitrary, divided by theta. So if you have like 1 over the, if you plotted y as a function of 1 over x, you get this kind of a curve, and that's sort of what I was looking for. So the slope, that's our y, is equal to a. I just threw that in there to scale it, and then is a over theta, which was like our x. And so I just wrote that out right here. There's our function, and theta is going to be in radians, so just wanted to make sure I pointed that out. So we've got this equation. We want to separate the variables, so the r's are on one side and theta is on the other side. So the r's are already here, but I'll just pull the d theta over to this side. And this is a slope, so we want to integrate it to get the actual function of the curve. So I integrate both sides, so I'm going to integrate from some initial radius r0 to some arbitrary r, and we're going to integrate theta from some initial value to some final value theta. So the integral of dr over r is just natural log of r, and the same thing for d theta over theta, natural log of theta. And then we're going to evaluate that from r naught to r, and this from theta naught to theta. So we take this value using this r minus this function using this r. Same thing for theta. And then we've got this a in the front. So with a property of natural logs, as if you have something minus something, it's the same thing as that divided by this. And same thing with the thetas. We have an a out front. And another property is if you have a value in front of this natural log, it's like the exponent here. So we can take that a up here. So we've got natural log theta over theta naught raised to the a. And in order for this to be equal to each other, this quantity has to be equal to that quantity. So r over r naught is equal to theta over theta naught raised to the a. And so here's a function for our radius. It's r naught times this quantity raised to the a. So the problem is then we need to know R naught, theta naught, and A, and we can calculate R. So we can choose some values like R max, that's going to be the radius of our turbine. Theta max, that's just whatever amount of angle that we want to cover with our wing. And we can choose a starting slope and a final or an initial radius. That would be near the hub, someplace down there. So we're going to choose those values, and then we have to solve for A. So we can take this expression up at the top here, take our slope, multiply by theta, and we've got our A. So we can solve for A, just using the slope at our theta max equal to A over theta max. And then to find theta naught, we can plug in our maximum radius and the initial radius that we've chosen, and we've got theta max, and we've got A now, so we just calculated A, so we can solve for theta naught. So we just take R max divided by R naught and raise it to the 1 over A power, and then you just have to take that quantity, bring it to the denominator here, and theta naught goes to the goes to this side of the equation. So anyway, we can solve for theta naught. And that's the function right here that I've used for my airfoils, or not airfoils, but the wings for the turbine. This is the spreadsheet I use to calculate the profile of the blades. I've got some inputs here. There's some parameters that we can just pick, like a minimum radius. I chose 20. Maximum radius, that's the radius of the turbine. And the slope at the extremity, that's change in the radius with radius times the change in the angle, r d theta. So it's going to start out with that small slope, and then the slope is going to increase and increase until it gets towards the root. And delta theta is how much of an angle that this blade occupies. So I've got 60 degrees here. Then I converted that 60 degrees to radians because everything should be in radians. So anyhow, we have to come up with these. Well, we picked R naught. We have to come up with A, and theta naught. So those are the two values we need. And what I do is I pick them over here on this side. And we see that to solve for A, all we have to do is take this initial slope and multiply it by theta max, and we get our A. So that's what I've got here. There's our slope, C3, times theta max in radians, and then I've got an estimate for A. Then we need theta naught, and so we need that value. So take R max divided by R naught, raise it to the 1 over A, and then pull it over to this side and solve for theta naught. So here we go, E4, there's theta naught, there's the ratio of our radiuses, raised to the 1 over A, that's this estimate that we had there. So there was a problem here in that now that we have theta naught, that takes away a little bit from this delta theta. So it would start eating away at the beginning angle here, and I didn't want that. I wanted this to be a true 60-degree arc here. So what I ended up doing is I made it, this is the initial estimate for A and theta naught. I made a new estimate. This time I take the slope, I take the slope, and then I times it, instead of just by delta theta in radians, this E4, I add this theta naught estimate. So I just modify A just a little bit, and then I do something similar for the estimate for theta naught. Just add that little smidge to this angle, and then instead of 1 over A as we calculated here, it's this new A that we calculated. And I just did that a bunch of times just so that it would converge. And then I take this this final value here that should be completely converged and duplicate it over here. Okay, so then I take this maximum angle, divide it into 30 parts, and convert it to radians, add that theta naught to it, and use this expression to calculate R. This R naught times theta over theta naught to the A. And then so I've got the R for each theta, and then to plot it I just take the R times the cosine of the angle, but instead of using this angle that has a little bit of theta naught added to it, I just use the original angle that doesn't have that adjustment. That way the first point always starts on the axis here, and it occupies exactly 60 degrees. So anyway, y is similar except you use sine. I rotate it a little bit, 120 degrees and 240 degrees, so I get, just for plotting these two other blades. And then I take the x and y values and I put them in columns for comma separated variable export, so that the CAD can upload the curve. So anyhow, that gives us some flexibility. We can come up with other curves if we want. If we want just a 30-degree blade, we can go 30 degrees, so now it's occupying less. But you see it's got the shallow initial slope, and then it has to curve over quite quickly. If we make that something larger, then it's much more gradual. I mean, we have a higher slope at the beginning, and so this is much more rounded. If we want to bring this end in a little bit, we can change R0. We can't make it negative, and we can't go to 0 because then we get division by 0 errors. But we can bring this in closer to the hub if we wanted to. We could make this 100 degrees if we want. So it goes a little beyond. And maybe we want a little less slope for that. So that makes some very deep pockets here. But you notice there's quite a small gap here, so I don't think this would be a good thing to do. But the blade that I'm using, I have 60 degrees, and I have a 0.15 slope initially. And I think I put that at 20, but it doesn't have to be, it could be 10. So this is the blade that I'm using right now.